Right. Okay. Any question? What do you mean by rigid now? Okay. So a lot of times when you see the word rigid now, you can relate. That's my purpose. Okay. Right. So from here, we are going to construct our multi-body or integrated. Okay, the word integrated, why I use the word integrated free body diagram, or I will call it multi-body. Okay, we are going to have an integrated. Okay, so I'm going to sketch here now our free body diagram. This is your point A. Okay. Over here is our point B, and over here is our point C. Okay. Now we know that the cable at point B and point C will be under tension. Yes or no? Right? We know, okay, it's known that the cables at B and point C will be under tension or tensile loading. Okay? So we know that over here, this is our 25 times 10 to the power 3, right? And because of the cable, so I'm going to sketch our cable. Okay, this is our cable at point C, right? And then a longer cable. This is our cable at point B. And because both of them are in tensile, right? Tensile deformation. Because it has to support the point load and the gradient distributed load. Okay. So tension means what? This will be going in this direction. Okay. From the cable. And when we apply Newton's third law, right? When we apply Newton's third law, over here, this will be, I'm going to call this one, this is your F C naught. Okay, so this is our point 0. This is also our point 0, point O. Okay, our FCO will be in the opposite direction. Okay, and this over here, by applying Newton's third law, again, action equal to reaction, same magnitude, different in direction. Okay, now the triangular load over there that you see, okay, the triangular load, where is it applying? Okay, so we have to find, okay, we have to find the equivalent load. Okay, we have to find the equivalent load, and the equivalent load will be somewhere around here. So this is the equivalent load. Okay, so the equivalent load, some of you might ask me, Eugene, what is that distance? Okay, what is that distance of the equivalent load? So the equivalent load distance, so from here over here, is 2/3 multiplied by the length of 6 meters. Okay, so 2/3 times 6 is equal to 4. And the distance from here to here is 1/3 multiplied by 6. Okay, so 1/3 times 6, 1/3 times 6 is equal to 2 meters. Okay, and the equivalent load, because this is a triangle, the equivalent load is the area of the triangle for now. Okay, so it's half multiplied by 20 times 10 to the power 3 multiplied by 6 in terms of length. So this is equal to half times 20 to the power 3 times by 6. 60 times 10 to the power 3 Newton. Okay. Now, why is that? Okay. Why for a triangular load is taken as 1/3? Okay. So I'm going to do again. I'm going to explain why that is the case. Okay. Why that is the case. Okay. As I said, all of you have different backgrounds. Some of you are civil engineering programs. Some of you are in manufacturing. Some of you are in architect. So you have seen this before. Good. Okay. But I like to explain this to students that have not seen it before or have forgotten. Okay. Or have forgotten. Okay. So I'm going to explain about the distributed load. Okay. So in general, there are two types of distributed load. Okay, in general, there are two types of commonly used distributed load. Okay, so one is known as uniformly distributed load. Okay, so for this case, you have a simply supported structure. Okay, this is your point A. This is your point B, and the load go this way, uniform distributed load. Okay, and you are given that this is omega Newton per meter. Okay. So if I'm going to sketch a distributed load diagram, graph, not a diagram. What you will see, okay, we will have our y-axis. This will be in omega, and on our x-axis, this is our x. Okay. So what it said, so this is x as in, so this is 0, 0. This is our x direction. Okay. So this is where our point A is. This is where our point B is. Okay. And over a distance of L, right, we have a uniformly distributed load. Okay. Up to here. And this is where our omega is. Okay. So the equivalent load is the area under the line. Okay, so it's this area over here. Okay, so to calculate the area, so the omega equivalent is equal to omega L. Okay, and then where it's loaded on, okay, because it's evenly distributed load, where it's loaded on. Okay, so this is our beam again. Okay, it's loaded exactly at the center. This is where our omega L is, and the distance from here to here is L over 2. The distance from here to here is L over 2. Okay? So this is for our evenly distributed load. The next one that I'm going to draw now is our gradient distributed load. Okay. So what do I mean by gradient? So gradient is like what you've just seen, right? So this is our a pin and a roller. This is our point A and our point B. And then now our load is on a gradient. Okay? Our load is on a gradient. And when you see the omega on a distributed load, is the omega of the largest load. Okay? So Newton per meter. Okay, is the omega of the what? Largest load. Okay, so for this case, we are going to construct our distributed load graph. Okay, so what we have again, we have our axis over here. Now you all have the idea, right? Okay, so this is your x, this is your omega, and then our distributed load now look like this. Okay, and the function over here is equal to omega as a function of L is equal to omega over Lx. That's a function. Okay, if you're later on we'll use more of this, but just a preview. So the equivalent load again is area under the area, or area under the curve. So it's a triangular. So we know the distance from here to here is L. The height from here to here is omega. So the omega equivalent is equal to half times by omega times by L. Okay, so omega L over 2. Okay, then where is it acting on? Okay, for now, just take this as a fact because of time. Later on, I'll explain to you why. Okay, so the load, the equivalent, will be acting down here. So this is your omega equivalent load. The distance from here to here is 2L over 3, and the distance from here to here is L over 3. For now, okay, just take it this distance. Later on, I'll explain, probably next week, I will explain why. Okay, I'll let you guys finish copying first. Okay. Yeah, I need another 10 more minutes on this example. The rest. Yes, right angle triangular load. Okay, I mean, yeah, other shapes we have to use the integration method, a deal, which I will teach later in class. Okay, I think I'll teach that on the last week of class. Okay. Okay, so I'd like to move on in this example. So I'll copy this whole diagram again. Okay, the free body diagram. Yeah, I'll copy this. And I like to have the question on my side also. Okay, just I can stare it for a bit if I get lost. Okay. So the next thing that we're going to do, now we have all this information. Okay.